What if the universe is living on borrowed time? Modern physics suggests that empty space, the vacuum surrounding every atom, every star, every galaxy might not be in its most stable state. We may be inhabiting a temporary configuration, one that could transition to something else entirely. The transition would be catastrophic and instantaneous. It would begin at a single point and expand outward at the speed of light, erasing everything in its path. There would be no warning signs, no time to prepare. Tonight, we journey into the invisible quantum fields that fill all of space, where physicists have discovered both the source of mass and the universe's potential fragility. In the decades before the 20th century, physics felt complete. Not finished in every detail, of course, but complete in spirit. The universe, as far as anyone could tell, was a grand machine. Given enough information, enough precision, enough patience, its future could be calculated and its past reconstructed. Space was a silent stage. Time flowed evenly. Matter obeyed rules that felt permanent. That confidence did not survive the century. The first cracks appeared quietly, in equations scribbled on paper, in measurements that refused to agree with expectation. But the real rupture came not from theory, but from history. Physics did not merely describe the modern world, it helped reshape it. And in doing so, it changed how physicists thought about the power of their own ideas. During the Second World War, science was pulled into the center of human conflict. Laboratories became military assets. Equations became weapons. Tens of thousands of scientists were absorbed into a single goal: to harness the deepest laws of nature for destruction. For years, fundamental research was put on hold, postponed by urgency and secrecy. When the war ended, the world exhaled. But the people who had built those weapons did not return to their old innocence. They had seen what abstract symbols could become when translated into reality. There is a moment, often described by those who were there, when the celebration faded, when the cheering stopped, when the implications set in. One physicist later recalled walking through a city street, watching ordinary life resume construction, traffic, conversations, and feeling a strange sense of unreality. How could people go on building a future, he wondered, when the rules of destruction had changed so fundamentally, when the scale of consequence had leapt beyond anything civilization had ever faced? Physics, once a detached pursuit, had crossed a line. And yet, when the dust settled, scientists did what they have always done. They returned to questions, to curiosity, to the quiet desire to understand how the universe works, not how to end it. In the late 1940s, a small group of physicists gathered to talk again freely, without clearance forms, without military oversight. They shared ideas that had been building in isolation for years. New mathematical tools emerged. New ways of thinking took shape. At the heart of this renewal was a radical shift in perspective. Reality, it seemed, was not made of solid things. The deeper physicists looked, the less substance they found. Atoms were mostly empty. Nuclei were collections of smaller constituents. Even those constituents, electrons, quarks, refused to behave like objects in the classical sense. They appeared and disappeared. They interfered with themselves. They occupied multiple possibilities at once. To make sense of this, physicists abandoned the idea that particles were fundamental. Instead, they turned to something more abstract and far more unsettling: fields. In modern physics, a field is something that exists everywhere, not as matter, but as a condition, a set of values assigned to every point in space and time. Temperature is a simple example. So is pressure. But the fields of quantum physics are stranger. They do not merely describe reality. They generate it. An electron is no longer a tiny bead flying through emptiness. It is a vibration in an electron field that fills all of space. A photon is a ripple in the electromagnetic field. Every type of particle corresponds to its own underlying field, quietly present even when no particles are detected. Space, once thought to be empty, became crowded. Every location in the universe is saturated with quantum fields, layered atop one another, mostly calm, occasionally disturbed. Matter is what happens when these fields ripple in just the right way. This shift solved many puzzles, but it created new ones. If particles are excitations of fields, how do they interact? What causes forces? Why do objects resist being pushed? Why do some particles carry mass while others do not? The emerging picture was elegant. Forces were not continuous pulls or pushes, but exchanges. When particles interact, their fields exchange energy through temporary disturbances, quantum messengers that transfer momentum and influence. These messengers came to be known as force-carrying particles. Light itself fit neatly into this framework. So did the force that binds atomic nuclei. Even the weak force, responsible for certain types of radioactive decay, found its place. But as the mathematical structure of this framework grew more refined, something deeply troubling emerged. According to the symmetries at the heart of these theories, all fundamental particles should be massless, not light, not electrons, not the carriers of the weak force. All of them should move at the speed of light, indifferent to resistance, incapable of forming stable structures. Clearly, that was not the universe we inhabit. Electrons have mass. Quarks have mass. The particles responsible for the weak force are astonishingly heavy. Something was missing. For a time, this gap was tolerated. Physicists adjusted their equations, added terms, made assumptions. The machinery worked well enough to predict experiments. And predictions are the currency of science. But beneath the success lingered discomfort. Why does mass exist at all? Why does empty space behave the way it does? And, most unsettling of all, why does the universe appear to sit so delicately balanced between possibility and catastrophe? These questions did not announce themselves dramatically. They surfaced in lectures, in side remarks, in papers that only a few specialists read closely. Sometimes they were delivered with humor, sometimes with understatement. One physicist, known for his sharp wit and legendary teaching, liked to disarm his audience before leading them somewhere dangerous. He spoke casually, confidently, as if the implications of what he was saying were perfectly ordinary. But hidden inside those calm explanations was a realization that would take decades to fully unfold. If the vacuum of space, the lowest energy state of all those fields, is not truly stable, then the universe may be living on borrowed time, not in the sense of an impending countdown, but in the sense of probability, a game of chance played on cosmic scales. This is where our story truly begins. Not with explosions, not with alarms, but with a quiet idea resting inside the mathematics of modern physics, waiting patiently to be understood. For centuries, physics had enjoyed a peculiar kind of moral distance. Its discoveries reshaped understanding, but rarely demanded immediate reckoning. The equations of Newton did not carry guilt. Maxwell's fields did not haunt their author. Even the strange revelations of early quantum mechanics felt safely abstract, confined to chalkboards and journals, far removed from daily human consequence. That separation did not survive the middle of the 20th century. When global war consumed nations, physics was pulled from the margins of intellectual life and placed at its center, not as a quiet observer, but as an instrument. Laboratories that once existed for curiosity became sites of urgency. Calculations that might once have taken years were compressed into months. Theory was no longer judged by elegance alone, but by effectiveness. The Manhattan Project was unprecedented, not merely in scale, but in structure. Tens of thousands of people, scientists, engineers, machinists. Administrators were bound together in secrecy, spread across deserts, mountains, and cities, all focused on a single task: extracting energy from matter itself. Many of the physicists involved understood, in principle, what they were doing. They knew the equations. They understood nuclear binding energy. They could calculate the release. But understanding something mathematically is not the same as witnessing it. That distinction became impossible to ignore on a July morning in 1945. In the desert, far from cities and coastlines, a device was placed atop a tower. Observers positioned themselves miles away, wearing protective goggles, lying on the ground, shielding their eyes. They had rehearsed the sequence. They knew the timing. They trusted the calculations. When the detonation occurred, the desert was transformed. Light arrived first, brighter than anything the human eye was meant to encounter, followed by a rising column of fire and dust that climbed into the sky with unsettling calm. The ground trembled. The air itself seemed to recoil. For a brief moment, theory and reality merged perfectly. One physicist, standing beside the project's scientific director, turned and spoke words that would later echo through history. The sentence was short, blunt, almost casual. It captured the instant when pride collapsed into awareness. In that moment, physics ceased to be hypothetical. Accounts from those present describe a strange emotional sequence. At first, exhilaration, relief that the device had worked, confirmation that years of calculation had been correct. Then, slowly, something else crept in, a realization that could not be expressed by numbers. What had been unleashed was not merely energy, it was consequence. In the days that followed, celebrations were held. Applause filled rooms. Champagne bottles were opened. But even as people congratulated one another, the mood began to shift. The implications extended far beyond the desert. The world had changed in a way that could not be reversed. One physicist later recalled sitting in a city restaurant, watching people through a window as they went about ordinary life, building, planning, laughing, and feeling a profound dislocation. The streets looked the same. The buildings stood as before. Yet, beneath it all, something fundamental had altered. The scale of destruction available to humanity had expanded beyond imagination. Why? He wondered. Were people still making plans as if the future were guaranteed? This sense of unease was not confined to a single individual. It rippled quietly through the scientific community. Physics had proven itself powerful in a way no previous generation had confronted. The equations worked, and because they worked, they demanded responsibility. For years, normal scientific life had been suspended. Research into fundamental questions was postponed. Conferences were canceled or repurposed. Ideas developed in isolation, scribbled in notebooks during rare moments of quiet, then tucked away under layers of classification. When the war finally ended, there was a collective exhale, but there was no return to innocence. Physicists did not simply go back to their desks and resume where they had left off. They returned, changed, more cautious, more aware that abstract thought could reshape reality with terrifying speed. And yet, despite the weight of what had happened, curiosity did not disappear. If anything, it intensified. There was a hunger to reconnect not just with colleagues, but with questions that were older, deeper, and less immediately dangerous. Questions about the structure of matter, about the nature of forces, about the fabric of reality itself. In the late 1940s, a small group of physicists gathered on an island off the coast, deliberately removed from the pressures of military oversight and classified research. The setting was modest. The conversations were anything but. This meeting marked a turning point. For the first time in years, physicists could speak freely. They could argue without fear of censorship. They could share half-formed ideas, make mistakes, revise assumptions, and rebuild the intellectual continuity that war had fractured. The atmosphere was electric, not because of spectacle, but because of release. Years of suppressed thought poured out in dense discussions that stretched late into the night. Participants later described the meeting as a dam breaking a sudden rush of ideas long held back. Among those present were figures who would later define modern physics. Some spoke with careful formality, presenting dense calculations step by step. Others approached the blackboard with a different energy, sketching diagrams, waving hands, letting intuition guide the mathematics rather than follow it. One such physicist stood out not because his talks were longer, but because they were shorter. He spoke quickly, almost casually, as if the mathematics were secondary to the picture in his mind. His diagrams looked simple, almost playful, but hidden inside them was a powerful idea that interactions could be visualized, that processes unfolding in the invisible quantum world could be tracked as exchanges. These conversations laid the foundation for a new way of understanding reality. Rather than treating particles as isolated objects, physicists began to see them as manifestations of something deeper. The focus shifted away from things and toward processes, away from entities and toward interactions. This was the beginning of quantum field theory. In this emerging framework, the universe was no longer a collection of tiny objects moving through empty space. Space itself was active, filled with underlying fields that existed everywhere at once. Particles were no longer fundamental. They were events, brief disturbances in fields that otherwise remained calm. An electron was not a bead. It was a vibration in an electron field that permeated all of space. A photon was a ripple in the electromagnetic field. Even when no particles were present, the fields remained, quietly defining what was possible. Forces, too, were reimagined. In classical physics, forces act directly. Objects pull and push each other across distance. In the quantum field picture, nothing happens directly. When particles interact, their fields exchange energy and momentum through fleeting disturbances, temporary ripples that carry influence from one place to another. These exchanges explained attraction, repulsion, decay, and transformation. They unified phenomena that had once seemed unrelated. Light, magnetism, radioactivity all became expressions of the same underlying logic. The success of this framework was undeniable. Predictions matched experiments with extraordinary precision. The theory worked, and yet, the better it worked, the more disturbing one of its implications became. At the heart of these equations were symmetries, mathematical rules that enforced balance and consistency. These symmetries were beautiful. They simplified calculations. They revealed deep connections between seemingly different forces. But they also imposed strict constraints. According to these symmetries, all fundamental particles should have no mass, not just light, which is famously massless, but electrons, quarks, and even the particles responsible for the weak force. Everything should move at the speed of light, indifferent to resistance, incapable of forming stable structures. This was not a minor discrepancy. It was a contradiction between theory and reality. At first, physicists treated it as a technical inconvenience, a detail to be resolved later. After all, the equations were producing correct answers. Perhaps mass would emerge naturally once the theory was fully developed. But as years passed, the discomfort grew. Mass was not optional. It was the reason matter could clump, bind, and persist. Without mass, there would be no atoms, no chemistry, no stars, no planets. The universe, described by the equations, would be unrecognizable. The unease was compounded by a deeper realization. If the most successful theories of physics could describe a universe radically different from the one we observe, then perhaps our universe is not inevitable. Perhaps it is one outcome among many, a configuration selected not by necessity, but by chance. In a century already marked by the fragility of human systems, this idea resonated uncomfortably. Physics had learned how to split atoms. It had learned how to release energies once confined to stars. Now, quietly, it was beginning to question the stability of reality itself. And somewhere within these questions, waiting to be articulated, was the possibility that the vacuum of space, the calm background of existence, might not be as permanent as it seems. At first glance, the world appears firm. The surface beneath your feet resists your weight. The objects around you hold their shape. Walls do not dissolve when you lean against them. Tables do not blur into air. Matter feels dependable, definite, unquestionable. It is this everyday reliability that makes the idea of physical instability so difficult to accept. The universe, whatever else it may be, seems solid enough. But physics has learned, again and again, that intuition is a poor guide to the deepest layers of reality. Long before anyone spoke of quantum fields, scientists had already begun dismantling the notion of solidity. Atoms, once imagined as indivisible building blocks, were found to be mostly empty space. Their nuclei, tiny and dense, occupied only a minute fraction of the volume they appeared to command. Electrons, rather than orbiting like miniature planets, existed as probability clouds spread out, uncertain, and strangely intangible. Yet even this picture, unsettling as it was, did not go far enough. Because atoms are not the bottom of the story, not even close. To continue downward, physicists were forced to abandon the idea that matter is made of things at all. The closer they looked, the more the language of objects began to fail. Particles did not behave like dots. They did not follow single paths. They did not possess well-defined properties until measured. Sometimes they appeared to be waves. Sometimes they interfered with themselves. Sometimes they vanished altogether. Trying to describe this behavior using classical concepts led only to confusion. So physicists changed the question. Instead of asking what particles are, they began asking what must exist for particles to appear at all. The answer was fields. In everyday language, a field is something simple and familiar. Temperature is a field. At every point in a room, the air has a temperature. Pressure is a field. So is humidity. These fields assign numbers to locations, creating a continuous background that objects move through. But the fields of modern physics are not passive descriptions. They are active entities. They do not merely record what happens, they determine what can happen. In the quantum picture, each fundamental particle corresponds to its own underlying field. There is an electron field, a quark field, a photon field, and many others. These fields exist everywhere, filling all of space, regardless of whether any particles are present. An electron, then, is not a thing traveling through emptiness. It is a localized disturbance, a ripple in the electron field. When that ripple moves, we say an electron has moved. When the ripple disappears, the electron is gone. The field remains. This inversion of perspective is subtle but profound. Particles are no longer primary. Fields are. Every location in the universe is permeated by a vast collection of quantum fields, layered atop one another, mostly quiet, occasionally excited. Space itself is no longer empty. It is crowded, restless, alive with latent possibility. This idea alone is enough to destabilize the notion of solid matter. What you experience as a rigid surface is not a continuous block of substance. It is the result of countless quantum fields interacting, exchanging energy, enforcing constraints. The resistance you feel is not the collision of solid objects, but the consequence of electromagnetic fields refusing to overlap in certain ways. At the most fundamental level, nothing ever truly touches anything else. Solidity, it turns out, is an emergent illusion. Even color, something that feels deeply tied to material reality, does not exist in objects themselves. Surfaces do not contain redness or blueness. They interact with electromagnetic fields, absorbing some wavelengths, reflecting others. The sensation of color is constructed in the brain, translated from raw physical signals into experience. Sound follows a similar pattern. The universe itself is silent. What you hear are vibrations interpreted by biological machinery. Without a listener, there is no noise, only oscillations. The deeper physics goes, the more reality begins to look like a translation layer rather than a direct presentation. And yet, despite this abstraction, the field picture proved astonishingly effective. It allowed physicists to calculate interactions with unprecedented accuracy. It unified phenomena that had once seemed disconnected. It explained why particles could be created and destroyed, why forces could act across space, why uncertainty was not a flaw but a feature. But it also demanded a radical rethinking of forces themselves. In classical physics, forces are direct influences. Gravity pulls. Charges repel. Magnets attract. The mechanisms are left vague, sometimes described metaphorically as invisible lines or fields acting at a distance. Quantum field theory replaces this vagueness with a precise, if counterintuitive, process. Forces arise through exchange. When two particles interact, their respective fields do not act directly on one another. Instead, the interaction generates a disturbance in another field, one associated with the force itself. This disturbance propagates between the particles, carrying energy and momentum. These disturbances are what physicists call force-carrying particles. Light, for example, is a ripple in the electromagnetic field. When an electron changes its state, it creates a ripple, a photon that travels through space and is absorbed elsewhere. The transfer of energy and momentum through this ripple is what we experience as electromagnetic interaction. The same logic applies to other forces. Each has its own field. Each field has its own characteristic ripples. This picture is elegant. It is symmetrical. It is mathematically precise, and it leads directly to a puzzle. If everything is a field, and particles are merely excitations of those fields, then the properties of particles must come from the properties of the fields themselves. Charge, for instance, reflects how a particle couples to a particular field. Spin reflects how it transforms under rotations. These attributes emerge naturally from the mathematics, but mass does not. According to the symmetries underlying the equations, particles should move effortlessly, unimpeded, at the speed of light. They should not resist acceleration. They should not weigh anything. The equations insist on this outcome with stubborn consistency, yet the universe does not comply. Electrons are slow compared to light. Quarks are heavier still, and the particles responsible for the weak force, the interactions that allow certain types of radioactive decay, are enormously massive by comparison. This contradiction could not be ignored. It was not merely a gap in understanding. It was a warning sign. If the most fundamental description of reality predicts a universe without mass, and yet we clearly live in a universe full of mass, then something crucial is missing. Either the theory is incomplete, or our understanding of the vacuum, the baseline state of all those fields, is flawed. This realization shifts attention once again, away from particles and even away from fields, toward the nature of empty space itself. In quantum field theory, the vacuum is not nothing. It is a state. the lowest energy configuration of all fields combined. But lowest does not necessarily mean simple, nor does it guarantee stability. A field can have multiple possible energy states. Some may be lower than others. Some may be separated by barriers, invisible in classical physics but permeable in quantum mechanics. This means that the vacuum we inhabit, the quiet background of reality, might not be the only possible one. It might not even be the best one. At this stage, the implications remain distant, almost philosophical. Physics has not yet invoked catastrophe. There are no expanding bubbles, no collapsing universes, no sudden endings. There is only a growing unease that the foundation of reality may be more conditional than previously assumed. Matter, once thought to be solid, has dissolved into probability. Particles, once imagined as objects, have become ripples. Space, once empty, has filled with restless fields. What remains is a question, hovering just beyond the mathematics. If everything depends on the state of these fields, what happens if that state changes? For now, the question is left unanswered, but it will not remain so for long. Once the idea of fields is accepted, forces can no longer be thought of as pushes or pulls in the ordinary sense. That older picture, objects tugging on one another across empty space, belongs to a universe that no longer exists. In the quantum view, nothing acts directly. Influence is always mediated. Every interaction is a conversation, conducted through the background of fields that fill all of space. This shift in perspective is subtle at first, but once seen clearly, it becomes impossible to unsee. Imagine two electrons approaching one another. In everyday language, we say that they repel. We picture an invisible force pushing them apart, some mutual aversion that increases as they draw closer. But in quantum field theory, this description is only a shorthand. What is actually happening is far stranger and far more precise. Each electron is not a tiny, charged object moving through emptiness. Each is a localized excitation in the electron field. When two such excitations come near, the combined disturbance they create does not act directly. Instead, it agitates another field entirely. The electromagnetic field, that agitation takes the form of a ripple. This ripple is brief. It does not persist. It is not directly observable in isolation, but it carries energy and momentum from one electron to the other. It is exchanged, and through that exchange, the electrons alter their motion. The ripple is what physicists call a photon. In this picture, a force is not a continuous influence. It is the cumulative effect of countless tiny exchanges. Each exchange is discrete, quantized, probabilistic. Together, they create the smooth behavior we experience at larger scales. This is not merely an interpretive trick. It is how calculations are actually performed. When physicists compute the likelihood of interactions, they do not imagine invisible pushes. They track the exchange of ripples between fields. This way of thinking did not arrive fully formed. It emerged gradually, shaped by necessity rather than preference. Early quantum theory struggled to describe interactions consistently. Calculations often produced infinity's nonsensical results that had to be discarded or manipulated away. The mathematics was powerful but unwieldy, elegant yet fragile. A breakthrough came when physicists realized that interactions could be decomposed into simpler processes, each involving the exchange of these temporary disturbances. Complicated interactions could be built from combinations of simpler ones. What had once seemed impossibly abstract became, at least conceptually, visualizable. Interactions could be drawn. These drawings were not literal pictures of reality. They were bookkeeping devices, ways of organizing calculations, but they carried intuition with them. And intuition is a powerful tool. In these diagrams, particles approach, exchange a ripple, and depart altered. Time flows in a direction. Energy and momentum are conserved at every step. The invisible becomes tractable. What mattered most was not the drawing itself, but the idea behind it. Forces are processes, not properties. The success of this framework was astonishing. It allowed physicists to calculate quantities with precision unmatched in any other area of science. Predictions agreed with experiments to extraordinary accuracy, sometimes to 1 part in a billion. Electromagnetism fit beautifully into this picture. The photon, massless and swift, carried influence across unlimited distances. The force weakened with separation, but it never truly vanished. Light could travel across galaxies. Electric forces could, in principle, extend forever. The strong force, too, found its place. Though in a more complex form, quarks exchanged ripples in a field associated with the strong interaction. These ripples, called gluons, did not merely transmit force. They interacted with one another, binding quarks together in an intricate, dynamic dance. This explained why quarks were never observed in isolation. The field itself conspired to keep them confined. So far, the story was coherent. Forces were unified under a common language. Fields exchanged ripples. Interactions followed rules dictated by symmetry. Then physicists turned their attention to the weak force. The weak interaction had always been an oddity. It was responsible for radioactive decay, for the transformation of particles from one type into another. It played a crucial role in stellar processes and in the early universe. Yet it behaved unlike any other force. Its reach was extraordinarily short. While electromagnetism and the strong force could act across atomic distances or beyond, the weak force operated over scales smaller than a proton. It was fleeting, localized, almost shy. In the exchange picture, this suggested an explanation. The ripples responsible for the weak force the messengers exchanged between particles were different. They were not light and nimble like photons. They were heavy, enormously heavy. In quantum field theory, the mass of a force-carrying ripple matters deeply. A massless ripple can propagate indefinitely. A massive one cannot. It borrows energy from the vacuum, exists briefly, then disappears. The heavier it is, the shorter its lifetime, and the shorter the distance it can travel. This is not a matter of engineering limitation. It is a consequence of the uncertainty built into the fabric of reality. Energy and time are linked. To create a massive ripple requires energy. That energy can be borrowed only for a limited duration. The more energy required, the less time is allowed. The weak force carriers known as the W and Z bosons are so massive that they can exist only for an extraordinarily brief instant. They barely have time to move before they decay. As a result, the weak force reaches only across tiny distances. This explained the weakness of the weak force. But it raised a far more troubling question. Why are these bosons massive at all? In the mathematical framework that successfully described electromagnetism and the strong force, force-carrying particles emerge naturally as massless. Their masslessness is not an accident. It is required by the symmetries that make the theory consistent. If those symmetries are preserved, the equations demand that the carriers of force weigh nothing. And yet, here were particles central to the structure of the universe that were profoundly massive. This was not a small discrepancy. It was a fundamental contradiction. One could not simply assign mass to these particles without consequences. Doing so by hand shattered the delicate balance of the theory. Calculations lost their predictive power. Infinities reappeared. The mathematical machinery broke down. The weak force existed. Its effects were measured. Its carriers were inferred, but their mass should not have been possible. Physicists found themselves trapped between two unacceptable options. Either the theory was wrong, despite its astonishing success elsewhere, or something deeper was at work, something that allowed mass to appear without destroying the underlying symmetries. This tension sat at the heart of modern physics for years. It was not always discussed openly. Sometimes it was sidestepped. Sometimes it was treated as a technical issue, to be resolved later, but it never truly went away. The problem was not limited to the weak force. It extended to matter itself. Electrons, quarks, and other particles also had mass. Not nearly as much as the W and Z bosons, but enough to matter. If mass could not be written directly into the equations without breaking them, then mass must arise indirectly. From where? The search for the answer led physicists back to the idea of symmetry. Symmetry, in physics, does not mean visual beauty. It means invariance, a property that remains unchanged under certain transformations. Rotate a system, and the laws remain the same, shifted in time, and nothing fundamental changes. These symmetries are not optional. They are woven into the structure of the equations. They dictate which interactions are allowed and which are forbidden. They protect certain quantities from change, and symmetries, when present, impose strict rules. One of those rules was clear: if the symmetry underlying a force remained intact, its carrier must be massless. To give mass to the weak force carriers without destroying the theory, something radical had to happen. The symmetry had to be hidden, not broken explicitly, but concealed. This idea symmetry that exists in the equations but not in the state of the system was deeply counterintuitive. Yet it had precedent. Physicists had seen similar behavior in other areas of science. A system could obey symmetric laws while settling into an asymmetric configuration. The universe itself might do the same. This realization marked a turning point. The problem of mass was no longer about adding terms to equations. It was about understanding the nature of the vacuum, about recognizing that empty space might not respect the same symmetries as the laws that govern it. If the vacuum itself behaved differently, if it possessed structure, if it carried a hidden preference, then particles moving through it might acquire mass naturally, without violating the deeper rules. This was not yet an answer. It was a direction, but it pointed towards something profound: the idea that empty space is not passive, that it can shape the behavior of particles simply by existing in a particular state. For now, the machinery of quantum field theory continued to work. Even with this unresolved tension, predictions remained accurate. Experiments continued to confirm the framework. But beneath the success lay an unresolved contradiction, waiting patiently. Forces could be described as conversations between fields. The language was elegant, the grammar precise, yet one word remained undefined: mass. And to understand where mass comes from, physicists would have to look not at particles, nor even at forces, but at the vacuum itself, at what space does when nothing appears to be happening. That is where our journey turns next. If one follows the equations of modern physics without prejudice, without intuition, without appealing to what the world seems to be, the conclusion is stark and unavoidable. The universe should not weigh anything, not in parts, not in total, not even in principle. The mathematical structures that successfully describe forces and interactions insist, with remarkable consistency, that fundamental particles must be massless, gliding effortlessly through space at the speed of light, unburdened by resistance or inertia. This is not a quirk of a single model or a fragile assumption that can be adjusted later. It is a consequence of symmetry, built deeply into the language that governs quantum fields. And because those symmetries are what make the theory predictive and stable, they cannot simply be discarded without unraveling everything else. The problem of mass, therefore, is not a missing detail. It is a contradiction between what the equations demand and what the universe unmistakably displays. To appreciate why this contradiction is so severe, it helps to return to a definition that predates quantum mechanics by centuries. one that remains quietly foundational even today. In classical physics, mass is not primarily about weight or substance, but about inertia, about how an object responds when a force is applied. According to Newton's second law, force is proportional to mass times acceleration, meaning that mass is the measure of an object's reluctance to change its state of motion. A heavy object is not heavy because it presses downward, but because it resists being pushed. This definition survives intact into modern physics, stripped of metaphor and grounded in behavior. When a particle has mass, it does not respond freely. It slows. It lags. It demands energy to be moved. Mass, in this sense, is not something a particle possesses like a label, but something it expresses through interaction. In the framework of quantum field theory, this definition becomes deeply problematic. Particles are excitations of fields, and fields themselves obey equations governed by symmetry. If a field respects a particular symmetry, then the excitations of that field must behave in ways consistent with it. One of the most important of these constraints is that symmetric fields give rise to massless excitations. The mathematics does not allow otherwise. To insert mass directly into the equations is to violate the symmetry. And when that happens, the theory begins to collapse under its own weight. Calculations that once produced precise results now explode into infinities. Predictions lose meaning, and the delicate cancellations that keep the theory coherent fail. Mass cannot simply be added as an afterthought. It must arise in a way that preserves the underlying structure. The tension becomes impossible to ignore when the weak force enters the picture. Unlike electromagnetism, whose massless carrier allows it to reach across vast distances, the weak interaction operates over an extraordinarily small range, confined to the heart of atomic nuclei. This behavior points directly to the mass of its carriers, the W and Z bosons, which are so heavy that they exist only fleetingly before decaying. Their mass explains the weakness of the force, but it also sharpens the paradox. According to the symmetries that unify the weak force with electromagnetism, these bosons should be massless, indistinguishable in that respect from photons. Yet experiments insist otherwise. The equations say one thing, nature says another, and neither can be easily dismissed. Physicists attempted, for a time, to sidestep the issue. Perhaps mass was not truly fundamental, but an emergent effect. Perhaps it arose from interactions in ways not yet fully understood. But every attempt to treat mass as a secondary correction ran into the same wall without a principled mechanism. The theory lost its internal consistency. The success of quantum field theory elsewhere made this failure more troubling, not less. A framework capable of predicting experimental outcomes with astonishing precision could not explain why the particles involved behaved as if space itself were resisting them. The universe seemed to be telling a coherent story, but one chapter was missing, and it was not optional. The discomfort deepened when physicists realized that the mass problem was not confined to exotic particles or obscure interactions. It applied directly to the matter that makes up everyday reality. Electrons have mass. Quarks have mass. Without it, atoms could not form stable structures. Chemistry would not exist, and stars could not ignite. The very possibility of complexity depends on mass. Yet, the most fundamental equations of physics appear to forbid it. This contradiction suggested that the source of mass could not lie within particles themselves, nor in the forces they exchange, but somewhere deeper, embedded in the structure of space itself. Attention therefore shifted toward the vacuum, a concept that had already been quietly transformed by quantum theory. In classical physics, empty space is truly empty, a passive backdrop against which events unfold. In quantum field theory, the vacuum is anything but nothing. It is the lowest energy configuration of all fields combined, a state that defines what counts as normal, what counts as stable. And what counts as possible. If particles behave differently in the vacuum than the equations suggest, then the vacuum itself must be doing something non-trivial. It must possess structure, or preference, or asymmetry, even if that structure is invisible. This realization reframed the mass problem entirely. Instead of asking why particles have mass, physicists began asking why the vacuum behaves as if it endows them with inertia. Instead of treating mass as an intrinsic property, it became something relational, something that arises because particles move through a background that is not as neutral as it appears. The question was no longer how to add mass to the equations, but how to understand the vacuum well enough that mass emerges naturally, without destroying the symmetries that make the theory work. At this stage, the universe stood at a crossroads of interpretation. Either the mathematical framework that had proven so successful was fundamentally flawed, or reality itself was hiding a subtle mechanism beneath the calm surface of empty space. The answer, whatever it was, would have to be elegant, because inelegant solutions had already failed. It would have to preserve symmetry while somehow denying its most obvious consequence. And it would have to explain why the universe looks heavy, slow, and structured, when every indication suggested it should have been light, swift, and empty. The path forward would require a radical shift in perspective, one that treated the vacuum not as a void, but as an active participant in the story of matter. It would require accepting that the universe, in cooling from its earliest moments, may have settled into a state that hides its own symmetries, leaving behind a residue we interpret as mass, and it would require introducing a new kind of field, one unlike the others, whose quiet presence everywhere could change everything without announcing itself. In physics, symmetry does not mean beauty in the everyday sense, nor does it refer to visual balance or pleasing patterns. Symmetry is something far more austere and far more powerful. It is the requirement that the laws of nature remain unchanged under certain transformations. Rotate a system, and the equations should still apply. Shift it in time, and nothing fundamental should alter. Change the way you label a field locally, and the physical outcomes should remain identical. These invariances are not aesthetic choices, they are structural demands, and from them flows some of the deepest truths we know about the universe. When physicists speak of symmetry, they are speaking about what reality refuses to care about. This idea took on formal weight through the work of a mathematician who did not set out to revolutionize physics, yet quietly did so anyway. Emmy Noether demonstrated that every continuous symmetry of a physical system corresponds to a conserved quantity. If the laws of physics do not change with time, energy must be conserved. If they do not change with position, momentum must be conserved. These were not assumptions or empirical coincidences, but mathematical necessities. With this insight, conservation laws ceased to be convenient rules and became unavoidable consequences of symmetry itself. From that moment on, symmetry was no longer optional, it was the engine of physical law. Quantum field theory absorbed this lesson deeply. Fields were not free to behave arbitrarily. They were constrained by the symmetries they respected. In particular, certain symmetries demanded the existence of force-carrying fields, known as gauge fields, whose role was to preserve invariance under local transformations. These gauge fields were not added by hand. They emerged inevitably from the requirement that the theory remain consistent when the internal parameters of fields varied from place to place. What had once looked like separate forces now appeared as manifestations of deeper symmetry principles. Electromagnetism was the simplest example. The equations describing charged particles remained unchanged when the phase of their quantum fields was altered, as long as that change was compensated by the presence of an electromagnetic field. This symmetry, subtle and abstract, forced the existence of the photon and dictated how it must interact. The photon was not merely a particle of light, it was the guardian of symmetry, ensuring that the laws of physics did not depend on arbitrary choices. In this sense, forces were no longer fundamental actors, but enforcers of mathematical consistency. The success of this approach encouraged physicists to look for similar structures elsewhere. The weak force, strange and elusive though it was, exhibited patterns that hinted at an underlying symmetry analogous to electromagnetism, but richer and more complex. Instead of a single degree of freedom, it required multiple internal components, linked together through a more elaborate gauge structure. When this structure was written down carefully, something remarkable emerged. The weak force and electromagnetism appeared not as separate entities, but as different expressions of a single, unified framework. This electroweak theory was a triumph of abstraction. It suggested that at sufficiently high energies, the distinction between electromagnetic and weak interactions disappears entirely. There is only one force, governed by a unified symmetry, with multiple gauge fields acting in concert. The familiar forces we observe are merely the low-energy remnants of this deeper unity, shaped by conditions that prevailed as the universe cooled. For a moment, it seemed as though physics had found a path toward the long-sought goal of unification, not through speculation, but through disciplined mathematics. Yet, the same theory that unified forces also sharpened the mass problem to an unbearable edge. Within the electroweak framework, the symmetry that bound the forces together was incompatible with mass. If the symmetry were exact and fully respected by the vacuum, then all associated gauge bosons would have to be massless. The mathematics allowed no compromise. Either the symmetry held or mass appeared, but not both at once. The universe, inconveniently, insisted on having both. This was not merely an aesthetic discomfort. Without mass, the weak force would extend indefinitely. Indistinguishable from electromagnetism, radioactive decay would behave differently. Stellar processes would not proceed as observed. The universe would not resemble the one we inhabit, yet introducing mass directly into the equations destroyed their consistency, undoing the very symmetries that made the theory predictive. Physicists were faced with a dilemma that felt almost philosophical in its severity. How could nature obey symmetric laws while producing asymmetric outcomes? The answer required a subtle distinction, one that does not arise naturally from everyday experience. A system can be governed by symmetric laws while occupying a state that does not display that symmetry. The laws themselves remain intact, but their manifestation does not. This idea was not foreign to physics, but it had never before been applied at such a fundamental level. It suggested that the universe could hide its symmetries, rather than destroy them outright. This concept, known as spontaneous symmetry breaking, appears deceptively simple when illustrated by analogy. Imagine a perfectly symmetrical situation, balanced in every direction, yet unstable. The system must choose a configuration, and once it does, the symmetry is no longer visible. Even though the underlying rules remain unchanged, the choice itself is not dictated by the laws, only permitted by them. What emerges is order without explicit instruction, structure without violation. Applied to the electroweak theory, this idea carried extraordinary implications. It suggested that the vacuum of the universe, the lowest energy state of all fields, might not respect the full symmetry of the equations that define it. The symmetry would still exist in principle, preserved in the mathematical structure, but hidden in practice by the state the universe had settled into. In such a vacuum, particles moving through it would behave as if the symmetry were broken, acquiring properties forbidden by the symmetric laws alone. Mass, in this picture, would not be inserted into the equations. It would arise as a consequence of the vacuum's structure. The gauge bosons of the weak force would become massive, not because the symmetry was destroyed, but because the vacuum no longer treated all directions in the internal symmetry space equally. The photon, associated with the remaining unbroken symmetry, would stay massless. The distinction between forces would emerge naturally, without tearing the theory apart. This solution was as elegant as it was unsettling. It implied that empty space is not neutral, not featureless, not inert. The vacuum would possess a kind of orientation, a preferred configuration that influences everything passing through it. Particles would respond to this background not by choice, but by necessity, their behavior shaped by the state of space itself. What appeared as mass would be the visible trace of an invisible asymmetry. At this stage, the idea remained abstract, more promise than proof. The mechanism by which the vacuum could adopt such a structure was not yet fully articulated, nor was it clear how such a vacuum could arise from the early universe without fine-tuning or instability. But the direction was clear. To resolve the mass problem without sacrificing symmetry, physicists would have to accept that the vacuum is an active participant in the story of reality. The universe, it seemed, was not governed merely by equations written on paper, but by the state in which those equations were realized. Laws could be symmetric, yet outcomes need not be. The calm surface of empty space might conceal a deep and consequential choice made in the earliest moments of cosmic history. To understand how such a choice could occur, and what kind of field could make it possible, physicists would have to introduce something entirely new, not another force, not another particle in the usual sense, but a field whose role was to shape the vacuum itself. A field that does not vanish when the universe cools, but instead settles into a non-zero presence everywhere. That field, and the moment it transformed the universe from symmetry to structure, is where the story now turns. In the earliest moments after the universe began, there was no meaningful distinction between the forces we recognize today. Temperatures were unimaginably high, energies so extreme that every particle moved as if mass were irrelevant, swept along at nearly the speed of light by the furious expansion of space. In that environment, the elegant symmetries written into the equations of nature were fully expressed, unbroken and unhidden. The electromagnetic force and the weak force were not separate entities, but different faces of a single unified interaction. There was no preference, no asymmetry, no structure to distinguish one direction from another. The universe, at that stage, was simple in its uniformity, even if violent in its intensity. As the universe expanded, however, it cooled, and cooling changes everything. Energy that once surged freely through all fields began to drain away, leaving behind quieter configurations. In most quantum fields, this process is uneventful as the available energy drops, fluctuations diminish, and the field settles toward a value of zero. Ripples fade, excitations disappear. What remains is silence, punctuated only by the occasional disturbance when a particle passes through. This behavior is so common that it became the default expectation for how fields should behave. A field, when left alone long enough, should empty itself. But one field, it was proposed, might behave differently, not because it violated the laws of quantum mechanics, but because its internal structure allowed an unusual outcome. This field would be simpler than most, described not by vectors or directions, but by a single number at each point in space, a scalar field, uniform in form, yet profound in consequence. Unlike other fields, its lowest energy state would not correspond to a value of zero, even when the universe cooled as much as it possibly could. This field would refuse to vanish. It would remain present everywhere, quietly filling space with a constant background value. To understand how such a thing could occur, physicists turned to analogy, not because the mathematics was unclear, but because the implications were difficult to visualize. Imagine a system balanced perfectly, symmetric in every direction, yet unstable. At high energy, it can hover in this delicate state without consequence. But as energy is removed, the balance becomes precarious. The slightest disturbance is enough to push the system away from perfect symmetry, forcing it to choose a direction it had previously ignored. Once that choice is made, the symmetry is no longer visible, even though the underlying rules that allowed all possibilities remain unchanged. In the case of this new field, the early universe held it poised in a symmetric configuration, analogous to a pencil balanced on its tip. At high temperatures, thermal agitation kept the pencil upright, preventing it from falling. But as the universe cooled, that support weakened. The balanced state became unstable. Eventually, inevitably, the field shifted, settling into a new configuration that minimized its energy. The moment of transition was not explosive or dramatic. It was quiet, global, and irreversible. The symmetry did not shatter. It simply disappeared from view. When the field settled, it acquired a non-zero value everywhere in space. This value, known as the vacuum expectation value, became a permanent feature of the universe. From that moment on, empty space was no longer empty in the ordinary sense. It was permeated by the quiet presence of this field, the same at every location, indifferent to time, yet profoundly influential. Particles moving through space could not avoid interacting with it, because it was already there, woven into the fabric of the vacuum itself. The consequences of this transition were immediate and far-reaching. The unified electroweak symmetry that had governed the early universe was no longer fully expressed in the vacuum. Some components of the symmetry remained intact, while others were hidden by the field's chosen configuration. As a result, the gauge bosons associated with the weak force began to behave differently from the photon. The symmetry that had once required all of them to be massless now permitted a separation. The photon remained untouched, free to propagate without resistance, while the other bosons encountered something new. As the W and Z bosons moved through the background of this field, they interacted with it continuously. This interaction made them resistant to acceleration, limiting their ability to propagate freely. In practical terms, they acquired mass. Not because mass had been inserted into the equations, but because the vacuum itself now opposed their motion. The weak force, once unified with electromagnetism, became short-ranged and distinct, its carriers heavy and fleeting. The symmetry was still present in the equations, but the universe no longer displayed it openly. This process, known as electroweak symmetry breaking, did not occur at a specific location or a specific time in the way ordinary events do. It happened everywhere. As the universe cooled past a critical threshold, there was no boundary, no front, no region left unchanged. The laws of physics did not change, but the stage on which they were realized did. From that point onward, the vacuum itself carried information, encoding a choice that shaped the behavior of every particle in existence. The field responsible for this transformation was not introduced lightly. Its existence was not a matter of convenience, but of necessity. Without it, the mass problem remained insoluble. With it, mass emerged naturally. Symmetries were preserved at a deeper level, and the structure of the universe became intelligible. Yet, the field's defining feature was also its most unsettling. It could not be turned off. Unlike other fields, it did not fade as the universe cooled. It became a permanent resident of space. Because this field filled all of space uniformly, its influence was universal. Any particle that interacted with it would acquire mass, the amount depending on the strength of the interaction. Some particles, like photons, did not interact at all and remained massless. Others, like electrons and quarks, interacted weakly and acquired small masses. The W and Z bosons interacted strongly and became heavy, mass, in this picture. was not a fundamental trait, but a measure of how deeply a particle was entangled with the vacuum itself. This interpretation transformed the meaning of inertia. When a particle resisted acceleration, it was not because it carried an intrinsic burden, but because it was moving through a vacuum that pushed back. Space had become active, sticky in a subtle way, shaping motion without exerting force in the classical sense. The vacuum was no longer a passive backdrop, but a medium with properties of its own. What we perceive as mass is the trace of that medium's quiet resistance. At first glance, this solution seemed complete. It explained why mass exists without breaking symmetry. It accounted for the behavior of the weak force and preserved the elegance of the theory. It aligned with observations and offered clear predictions. The universe, it appeared, had solved its own paradox by choosing a vacuum that hid its symmetries while honoring them in principle. But hidden beneath this success was a question that few initially dared to ask. If the vacuum structure determined the masses of particles, then the precise value of the field filling space mattered enormously. Why did it settle where it did? Why not at a different value? Why not at zero? Or at some deeper minimum of energy? The equations allowed multiple possibilities. The universe had chosen one, and once that question was raised, it became impossible to ignore. Because if the vacuum had chosen a particular state, then that state might not be unique. It might not even be permanent. The field that refused to turn off might, under the right conditions, choose differently. The implications of that possibility would not become clear until much later, when physicists began to ask not how the field gives mass, but how stable its chosen state truly is. And in that question lay the seed of a far darker realization, one that would take decades to fully articulate. That realization, and the man who first grasped its significance, will carry us forward. At first glance, it is tempting to conclude that the field we have just encountered is responsible for all the weight in the universe. After all, it endows particles with inertia, slows them down, and allows matter to form stable structures. But this conclusion, while intuitive, is incomplete. The field that permeates space does not account for most of the mass you carry, nor most of the mass locked inside the atoms around you. Its role is foundational, but not dominant. To understand where the majority of mass truly originates, physics must look not to a single field, but to the restless dynamics unfolding deep within matter itself. Consider the proton, one of the fundamental building blocks of every atomic nucleus. It is composed of 3 quarks, bound together so tightly that they never appear in isolation. Each of these quarks does possess a small intrinsic mass, arising from its interaction with the vacuum field that fills space. But when physicists add those masses together, the result is startling. The combined mass of the quarks accounts for only a tiny fraction of the proton's total mass. Something else, far larger, is contributing the rest. That something is energy, not energy as we encounter it in daily life, but energy in its most compressed and persistent form. Inside the proton, quarks are locked in a constant exchange mediated by another field entirely, the field associated with the strong force. This force is carried by particles known as gluons, whose name reflects their role in binding quarks together. Gluons are massless in the traditional sense, yet they carry energy and momentum, and they interact not only with quarks, but with each other. The interior of a proton is not calm or static. It is a seething, dynamic system where energy is continually stored, exchanged, and confined. The strong force behaves unlike any other interaction in nature. Instead of weakening as quarks are pulled apart, it grows stronger, tightening its grip and preventing separation. As a result, quarks are trapped, and the energy of their confinement increases. Quantum fluctuations give rise to fleeting quark-antiquark pairs that appear and vanish, adding to the complexity of the system. The proton becomes a storm of activity, with energy coursing through it incessantly. And because energy and mass are equivalent, this energy manifests as weight. This equivalence, captured succinctly in Einstein's relation between mass and energy, is not a philosophical statement, but a physical one. Energy confined to a region of space behaves exactly like mass when it comes to inertia and gravity. The proton resists acceleration not because it contains heavy components, but because it contains enormous energy packed into a tiny volume. Remove that energy, and the mass would disappear with it. What we call mass, in this context, is simply energy that has nowhere to go. This insight reshapes our understanding of ordinary matter. The mass of your body, the weight of the Earth, the heft of stars and planets, arises largely from the energy of the strong force operating within atomic nuclei. The quarks themselves contribute only a small share. The rest is the cost of keeping them confined, the price paid to maintain structure against the rules that would otherwise let them drift freely. Matter is heavy not because it is made of massive pieces, but because it is made of tightly bound ones. Yet this does not diminish the importance of the field that gives particles their intrinsic mass. Without it, quarks would be massless, moving at the speed of light, incapable of being confined in the first place. Electrons would not settle into atomic orbits. Chemistry would fail before it could begin. The energy of the strong force would have nothing stable to act upon. The field that fills the vacuum provides the stage, while the strong force provides the drama. One makes structure possible, the other supplies its weight. This layered origin of mass reveals a universe far more intricate than early physics ever imagined. There is no single source, no solitary mechanism that explains why things are heavy. Instead, mass emerges from the interplay between vacuum structure and dynamic confinement, between fields that refuse to vanish and forces that refuse to let go. The solidity of matter is the outcome of balance, not simplicity. It is a compromise struck between competing tendencies in the laws of nature. At this point in the story, it might seem that the puzzle of mass has been fully resolved. We know how particles acquire inertia. We know why composite objects are heavy. We can trace the weight of the universe back to identifiable mechanisms grounded in well-tested theory. And for a time, physicists were satisfied with this understanding. The machinery worked. The explanations fit the data. But beneath this apparent completeness, another question was quietly forming. If the vacuum field sets the scale for particle masses, and if that scale determines everything from nuclear stability to stellar lifetimes, then its precise value is not arbitrary. A slightly different value would yield a radically different universe. The field could have settled elsewhere. The equations do not forbid it. This realization shifted attention once again, away from what the field does, and toward why it does it in exactly the way it does. Why does the vacuum possess the value it has? Why does it not relax further, toward a lower energy state? Why is the universe balanced so delicately between possibility and collapse? Those questions do not concern mass directly. They concern stability, and to confront them, physics would have to examine the field itself, not as a giver of mass, but as a dynamical system with its own potential, its own landscape, and its own vulnerabilities. That investigation would lead to a conclusion far more unsettling than any previous paradox, because it would suggest that the vacuum we inhabit, calm and uniform though it appears, might not be the deepest or safest state available. And once that possibility is taken seriously, the fate of the universe itself becomes uncertain. For many years, the field that filled the vacuum was treated as a solved problem. Its role was clear, its consequences measurable, its presence indispensable. The equations worked, experiments agreed, and the universe appeared stable enough to ignore deeper concerns. But theoretical physics has a habit of returning to questions that were once set aside, not because they were answered, but because they were assumed. And in the late 1970s, one physicist decided to look again, not at what the field did, but at why it did it in precisely the way it did. Sidney Coleman was not known for alarmism. He spoke carefully, often with humor, and preferred clarity over drama. Among his peers, he was respected not only for his technical brilliance, but for his ability to see where others had stopped looking. He was the kind of physicist who asked questions that seemed harmless until one followed them to their logical conclusion. And the question he asked about the vacuum was deceptively simple. Why should the field that fills space settle at the value it has, rather than at some other value allowed by the equations? To explore this question, one must think not in terms of particles or forces, but in terms of energy landscapes. Every field can be associated with a mathematical surface that assigns an energy to each possible configuration of the field. Some configurations are higher, some lower. The field, left to itself, will always seek the lowest energy available, just as a ball placed on a landscape will roll downhill until it can descend no further. This picture is not an analogy imposed from outside. It is embedded directly in the equations that govern field dynamics. In the simplest case, there is only one valley, one lowest point, one true minimum. The field rolls down and settles there, permanently stable. But Coleman noticed that nothing in the mathematics required the potential to be that simple. It could have multiple valleys, separated by ridges or barriers. Some valleys could be deep and global, others shallow and local. A field might settle into a local minimum, not because it is the lowest possible state, but because it is trapped there by the shape of the landscape. In a classical world, this would not be alarming. A ball resting in a shallow dip would remain there indefinitely unless pushed. Barriers would be absolute. The local minimum would be as good as permanent. But the universe is not classical at its foundation. Fields are quantum objects, and quantum systems do not respect absolute barriers. They leak, they fluctuate. They possess a non-zero probability of transitioning between states that classical reasoning would forbid. This phenomenon, known as quantum tunneling, is subtle but unavoidable. A quantum system described as a wave is never perfectly localized. Its influence spreads, even into regions that appear inaccessible, given enough time. A system trapped in a local minimum has a chance, however small, to penetrate the barrier and emerge in a lower energy state. For most everyday systems, this probability is negligible. For fields that define the structure of reality itself, the stakes are far higher. Coleman realized that if the vacuum field were sitting in a local minimum rather than the deepest one, then the universe would be living in what physicists call a false vacuum. It would appear stable. Its laws would be consistent. Its structures would persist. But beneath that calm surface would lie the possibility of decay. Not gradual decay, not erosion over time, but a sudden, catastrophic transition to a lower energy state. Such a transition would not occur everywhere at once. It would begin at a single point, a tiny region where the field managed to tunnel through the barrier. In that region, the field would drop to its true minimum, releasing an enormous amount of energy. This region would form a bubble of new vacuum, embedded within the old. And once formed, that bubble would not remain small. Driven by the energy difference between the false and true vacuums, the bubble would expand. The equations predict that it would do so at a speed approaching that of light itself. There would be no warning signal propagating ahead of it, no advanced disturbance detectable by instruments. If such a bubble were created anywhere in the observable universe, and if it were expanding toward us, we would not know until it arrived. Inside the bubble, the rules of physics would be different. The values of fundamental fields would change. Particle masses would shift. Forces might strengthen or weaken. The delicate balances that allow atoms to exist could be destroyed entirely. Chemistry, as we understand it, might become impossible. Matter might fail to bind, or worse. The new vacuum could induce rapid gravitational collapse, crushing whatever lay within it. From the perspective of an observer in the old vacuum, the transition would be instantaneous. One moment, the universe would be as it always was. The next, it would be gone. There would be no sensation of destruction, no experience of catastrophe. The laws governing experience itself would cease to apply. The end would be complete, silent, and final. This was not a speculative doomsday scenario dreamed up for effect. It was a direct consequence of taking quantum field theory seriously, of following its logic without flinching. Coleman emphasized that such a decay was a matter of probability, not inevitability. The false vacuum could persist for timescales far longer than the current age of the universe. But probability, by its nature, never guarantees safety. The unsettling implication was clear. Stability was no longer absolute. The universe could be long-lived, yet ultimately fragile. Its continued existence dependent on the unlikely but ever-present chance that the vacuum might choose differently. The calm of space was not proof of permanence. It was merely the absence of transition. So far, for a long time, this realization remained largely theoretical, discussed in specialized papers and advanced lectures. There was no way to know whether our vacuum was truly false or genuinely stable. The mathematics allowed both possibilities. The question could not be answered without information about the field itself, its mass, its interactions, the precise shape of its potential, and that information would remain inaccessible until an experiment of unprecedented scale and energy finally brought the field into direct view. For decades, the ideas surrounding vacuum decay and false stability remained suspended in abstraction, elegant yet untestable, unsettling yet safely distant. Physicists could sketch potentials, calculate tunneling rates, and debate probabilities, but they lacked a crucial ingredient: direct knowledge of the field itself. Without knowing its mass and precise behavior, the shape of the vacuum landscape could only be guessed. The universe might be safely nestled in a deep minimum, or it might be balanced precariously on a ledge, indistinguishable in everyday experience. The question was not philosophical. It was empirical, and answering it would require energies never before reached by human machines. That machine took shape beneath the countryside, on the border of two nations, buried deep underground in a circular tunnel stretching for many kilometers. Its purpose was not destruction, but revelation. By accelerating particles to near the speed of light and colliding them head-on, physicists hoped to recreate conditions closer to those of the early universe, where hidden fields might briefly reveal themselves. The energies involved were immense, concentrated into volumes smaller than atomic nuclei. For the first time, the vacuum itself would be probed, not indirectly through theory, but through experiment. When the long-awaited signal finally emerged from the data, it did not arrive as a dramatic image or a sudden flash. It appeared instead as a statistical whisper, buried beneath mountains of noise, discernible only after years of careful analysis. The decay patterns matched what had been predicted for the long-sought particle associated with the vacuum field. Its mass could be measured, its existence confirmed. The field that refused to turn off was no longer hypothetical. It was real. With that measurement came the ability to ask a more dangerous question. The stability of the vacuum depends sensitively on the mass of this particle and on the mass of the heaviest known fermion, the top quark. Together, these values determine the shape of the vacuum potential, whether it curves gently upward, dips shallowly, or slopes away into a deeper abyss. The mathematics is unforgiving. Small changes in these numbers can shift the universe from absolute stability to inevitable collapse. When physicists performed the calculation using the measured values, The result was neither comforting nor catastrophic. The vacuum did not appear to be perfectly stable, nor did it appear destined for immediate decay. Instead, it occupied a narrow and unsettling category known as metastability. The universe, according to the best data available, resides in a state that is stable enough to persist for vast spans of time, yet not guaranteed to be eternal. It is balanced, delicately, between permanence and transition. In practical terms, this means that the probability of vacuum decay is extraordinarily small. Timescales far exceed the current age of the universe by many orders of magnitude. Stars will burn out, galaxies will drift apart, and black holes will evaporate long before the vacuum is expected to change. From a human perspective, and even from a cosmic one, the danger is negligible. Yet negligible is not the same as zero. And in physics, zero is a very special number. The unsettling aspect of metastability is not that destruction is imminent, but that it is possible at all. The laws of nature do not promise permanence. They offer only likelihood. The universe persists not because it must, but because, so far, it has not done otherwise. The calm of empty space is not a guarantee. It is an observation, and observations, no matter how long they last, are not proofs. This realization casts the universe in a different light. Existence itself becomes a kind of extended pause, a long moment between alternatives. The structures we observe, atoms, stars, life, are not inevitable outcomes written into the fabric of reality, but contingent phenomena arising from a particular vacuum choice. Had the field settled elsewhere, none of this would exist. And should it ever settle elsewhere again, none of this would remain. Physicists are careful not to dramatize this conclusion. There is no evidence that vacuum decay has occurred anywhere within our observable universe. There is no indication that it is approaching. The equations suggest patience, not panic. And yet, the knowledge lingers, quiet and inescapable. The universe is not guaranteed to persist in its present form forever. Stability, like mass, is something that emerges, not something that is assured. In reflecting on this, some physicists have taken a stoic view. If the vacuum were to decay, there would be no suffering, no awareness, no time to regret. The transition would erase the very conditions required for experience. From within the universe, it would be the gentlest of endings, instantaneous and complete. From outside, if such a perspective were meaningful, it would be merely a change of state, a rearrangement of fields. And so, in the end, the story circles back to its beginning, a quiet idea, spoken calmly, with no urgency and no threat, yet carrying implications vast enough to encompass all of existence. The universe may be strong enough to last for trillions of years, or fragile enough to vanish without warning. Both possibilities are written into the same equations. Both are allowed. Neither is promised. What remains is not fear, but perspective, that everything we know rests on conditions that did not have to be, that the calm background of reality is not inert, but chosen, and that the greatest weakness of the universe, if it has one at all, is not instability, but contingency. For now, the vacuum holds. Space remains quiet. The fields remain as they are, and within that silence, matter continues to exist, to organize, and, briefly, to wonder why it is here at all. This is where we pause, not because the story is finished, but because the universe, for the moment, has chosen to continue. Tonight, nothing collapses, and nothing announces itself. The fields remain settled, particles move as they always have, and mass continues to exist as a quiet agreement written into the structure of space. The universe carries on without urgency, balanced on principles that are at once stable and uncertain, reliable yet never entirely fixed. What holds everything together is inseparable from what allows it to change. The same uncertainty that makes decay possible is also what permits atoms to form, matter to persist, and structure to emerge at all. Stability is not the opposite of fragility, but something that arises from it, carefully arranged rather than guaranteed. For now, the vacuum holds. Space remains calm, and the invisible fields continue their silent work across the darkness, just as they have for nearly 14 billion years. That is enough for tonight. Rest well,